we have the function f from r cubed to r squared, f of x, y, z equal to x minus 2y plus z, x squared plus y minus z. Let's calculate the differential of f in minus 1, 1, 1. As we know, the differential of f in minus 1, 1, 1 is a linear application which is defined from r cubed to r squared. Analyzing f, we can see that f is a function with two coordinates, f sub 1 of x, y, z and f sub 2 of x, y, z. As I said before, the differential is a linear application, and we are going to calculate the matrix of this application respect the canonical basis, and from there we will obtain the differential. As we know, the matrix of the differential respect the canonical basis is the Jacobian matrix. In this matrix, in the first column, we have to write the image of the first vector of the canonical basis 1, 0, 0 by the differential of f in minus 1, 1, 1. That is the same as derivating respect the first variable. This is derivating respect x. So the first column, we have to derivate f sub 1 and f sub 2 respect x in minus 1, 1, 1. In the second column, we would write the image via the differential in minus 1, 1, 1 of the second vector of the canonical basis. That is, derivating each coordinate of f respect the second variable y in minus 1, 1, 1. Finally, in the third column, we would write the differential in minus 1, 1, 1 of the third vector of the canonical basis. This is the same as calculating the partial derivatives respect the third variable z in minus 1, 1, 1. Let's calculate all the elements of this matrix, so we will obtain the Jacobian matrix. Let's do it down here. The derivative of f sub 1 and f sub 2 respect x. The first derivative is the derivative of f sub 1 respect x, so the derivative of x is 1 minus the derivative of minus 2y, as there's no x in here, this is 0, plus the derivative of z, which is also 0. So it is just equal 1. The derivative of f sub 2 respect x would be 2x. Substituting both in minus 1, 1, 1, this is x, this is y, and this is z. As everything's constant here, this is just 1, and on the second derivative it would be 2 times minus 1, that's minus 2. Let's write them both in the matrix, 1 and minus 2. Now, let's derive respect y. F sub 1 respect y would be the derivative of x is 0, the derivative of minus 2y is minus 2, and the derivative of z is 0. So this is minus 2. The derivative of f sub 2 respect y, it would be equal 1. So as everything's a constant, when substituting in minus 1, 1, 1, we would have the same numbers, minus 2 and 1. Finally, derived in respect z, f sub 1 derived respect z would be equal 1, and f sub 2 respect z would be minus 1. Substituting as they are constants, we obtain the same numbers again. 1 minus 1. Having a look at the left part of the screen, we can see that the differential of f in minus 1, 1, 1 goes from r cubed to r squared, so it would act over an element of r cubed. Let's call it h, k, and l. And the result is going to be in r squared. As we have the Jacobian matrix of f respect minus 1, 1, 1, we have the matrix of the differential in minus 1, 1, 1 respect the canonical basis. So, for calculating images, we will use this matrix. We will multiply this matrix by, as we have to calculate the image of HKL, and HKL is in the canonical basis too, we just multiply via column matrix with HKL. The first one is a matrix 2 times 3, and the second one is a 3 times 1, so they can be multiplied, and the result would be a matrix 2 times 1, 2 rows and 1 column. So we would have 1 times h minus 2 times k plus 1 times l, and the second row would be minus 2 times h plus 1 times k minus 1 times l. So the differential from r cubed to r squared of f in minus 1, 1, 1 acting over an element HKL would be an element in r squared, which would be h minus 2k plus l and 2 minus 2h plus k minus l.